We are moving along quite nicely, guys. We have finally reached our final unit, the Intermolecular Forces. So this is the last stuff that we need to get all of our 5s on the AP exam. So let's go ahead and jump right in. So we're talking about intermolecular forces. We've already been talking about intramolecular forces, and I just need you guys to recognize the difference here right off the bat. First, I listed the intramolecular forces. These are the bonds that we should be most familiar with: ionic bonding, covalent bonding, metallic bonding. These are the types of bonds that occur between two different elements. So for example, if you have a water molecule, you have an O that is covalently bound to an H and covalently bound to another H. This bond is between the atoms and it is part of the molecule. These are intramolecular forces. Okay, so this is be ionic, covalent, and metallic. Now an intermolecular force occurs between two different molecules. So if I bring another water molecule in here, we know that once again we have intramolecular forces here, but there's also going to be an attractive force between these two. And we have talked about this before. We have called this hydrogen bonding. Hydrogen bonding is occurring between the slight positive we have on the hydrogen and the slight negative we have on the oxygen. So it is between the molecules. This is an example of an intermolecular force. Now when it comes to intermolecular forces, ionic bonds actually fit in that category as well. So let's take a look at some of our intermolecular forces. So when it comes to the intermolecular forces, the hydrogen bonds that we mentioned up above and that we've seen in other units are shown right there. That's the one that most of us are familiar with. We all pretty much know what ionic bonds are as well. So with ionic bonds, they're kind of interesting in that you have something like this, an Na plus is ionically bound to a Cl minus, but then they're always in a lattice, they're always in a crystal. So then you would have another one right here, another salt particle right here. And so while we say maybe they're ionically bound right here and right here, well, there's also some attraction between those two right here and right here. So it's both an inter and an intramolecular force, which makes this guy the number one in terms of strength. Now, down below, we've also mentioned this word before, van der Waals forces. Van der Waals forces was something that we talked about when we were talking about gas laws. And we said that when you're talking about a real gas, sometimes when the particles get too close together, the gas laws stop working. And it's because we make some assumptions when we're talking about gases. We say that they're so small that they have no volume, but in reality the nucleus does have a little bit of volume. And we also say that they have no attractive forces, but we know that that's not true. If you put too much pressure on them, or you get them too cold, and the molecules get close together, they stop acting like a gas and will actually turn into a liquid. And we said that it was because of van der Waals forces. Well, now we're just sort of opening that up. What is a van der Waals force? Well, van der Waals forces are the collection sort of all of these intermolecular forces, hydrogen bonding being one of those things. So hydrogen bonding up until now, we have mainly focused on the H and the O. We say that there's a huge electronegativity difference between these, and that electronegativity difference gives us a slight negative here and a slight positive here. Now, I say slight, but as far as electronegativity differences go, this is that area that's approaching a difference great enough that it's almost ionic. It's sort of right on the borderline there. And there's actually two other combinations that will do that. H and N and H and F. And if you look at the periodic table, these guys are all clumped right together on the periodic table. So an H in combination with any one of those three gives us a large enough electronegativity difference that it's almost ionic, and so it's pretty significant, and we call it hydrogen bonding. Okay. Now, what if it's not that big? What if it's an electronegativity difference that's obviously making it polar, but not big enough that it's approaching ionic, right? Maybe it's a difference of 1, right? Remember that as we're looking at the electronegativity differences, 0 to 0.4 is non-polar covalent, 0.5 to 1.6 is polar covalent, and then 1.7 and above is ionic. So we're looking at fairly large differences with these three here, putting us closer to this range. So what if it's closer to this range right here? Well, then it's just what we would call a dipole-dipole. And then what if it falls in this area? What if it's not polar at all? Well, there's still some attractive force there, and we call that London dispersion forces. Okay, so we've got 3 different types. Now, we have spent plenty of time this year talking about ionic, talking about dipoles, talking about hydrogen, but this guy right here, right, this one, the London dispersion forces, this is a new word for us. So we're going to look at this one a little bit closer. This is what we see happening between non-polar materials. Let's go to this guy. So when we're looking at London dispersion forces, they are found in anything that has electrons. So basically all molecules have these. When we talk about non-polar materials, this is the only attractive force that they have. But if you have something like NaCl, right? NaCl is going to basically have ionic attractive force, but it is also going to have London. London exists in everything. And then it's also possible to have some hydrogen bonds thrown on there or ionic bonds thrown on there, etc. Now, the way that a London dispersion force works is it works through these 2 situations here, instantaneous dipoles and induced dipoles. So it still is going to come down to a dipole a little bit here. Now, what we have happening, let's say that we have something like nitrogen. So let's say that I have a nitrogen molecule. We know that a nitrogen is a triple bond to another nitrogen. And we know that there maybe is another nitrogen gas over here. And so we know that these things are perfectly non-polar, right? Diatomic molecules are about as non-polar as you could possibly get. So when we're talking about nitrogen, we know that there are some electrons that are around the nitrogen, right? You have some in the 1s, you have some in the 2s, you have some in the 2p. And so I'm not going to draw them all in, but we have some electrons that are flying around nitrogen atoms in these particular orbitals that they've got going on here. Now, when this is happening, we know that electrons move in random and chaotic patterns. They're moving in these sort of wave-like motions. They have areas of probability, but they are not locked into those areas, right? It's just a 90% chance that we find them in the S cloud or in the P cloud or wherever that is. And so occasionally, just through random chance, you might end up in a situation where you have more electrons on one side of a nitrogen than you do on the other, right? So just through random motion, random chance, for a brief moment in time, because we know it's not going to want to stay like this because you have too much negative, they're going to try and spread themselves out. But just through random motion for a brief moment in time, we get a negative that pops up on this side of the molecule. Now, this is what we call an instantaneous dipole. For one instant, we get a negative on that side, which means that this side becomes positively charged. Now, what that does is, because if the neighbor is close enough, remember with our gas laws, the only time that this worked was if the particles were under super high pressure or very low temperatures, right? Because they had to get them in close proximity to one another. If it's not close, this doesn't happen. But if these two nitrogens are very close together, what is going to happen if you drop a positive right there. Well, these electrons right here are going to respond to that. And what happens is maybe one of these electrons gets pulled up here. And what did we just do? We induced a dipole in the neighboring atom. Induced means you caused something to happen. So now all of a sudden this gets a negative and this gets a positive, and what do these two molecules do? They stick together. Okay, so we have this random motion of electrons here, and then it causes an arrangement or a situation to form in the neighboring atom, and they stick. And then after a second goes by, this one goes up here, says, wait, my electrons are messed up. Let's fix this. And so all of a sudden, this electron jumps back down where it belongs. So we'll put it back down here. And all of a sudden, is this side negative anymore? No. So this evaporates away, which causes this one to evaporate away. And then all of a sudden this one says, hey, why am I hanging out over here? There's nothing pulling me. And so it goes back. And what happened to all my charges? They all fell apart. And so the attraction that I was feeling right in this area is now gone. And so these are fleeting. London dipoles, London dispersion forces, they turn, it's like turning off and on completely all the time. Off, on, off, on, off, on. So while this one is now off, guess what? This guy over here might be starting to get out of balance. And so if this one gets out of balance, it's going to create an attractive force between this one. And so this one turns on. And then all of a sudden this one shuts off. And all of a sudden this one turns back on. Right? Now in something like this, we could see this is probably going to have trouble getting into a rotation like this. Right? What are the odds that it gets out of balance? Not great. And so we see in real life, does nitrogen form a liquid by sticking together very easily? No, right? Nitrogen has a really difficult time with this because you only have two atoms that could be either off or on. So if you want London dispersion forces to become more potent, what are some things that we could do? Well, we can make the chain longer. So let's take a look at this. So if we want to influence these London dispersion forces, we basically need more electrons here. We need more options, more probability, more chances for the atoms to get out of balance. So instead of two atoms, let's say that you have a chain. 1, 2, 3, 4, 5, 6, 7, 8. A chain that's 8 long. This is going to have, so 8 is what? 8 is octane. And we know that octane is a liquid. This is what you put in your gas tank of the car, right? So you go, oh, okay, now all of a sudden, when these things line up, you can say, oh, in one brief second, maybe this one is on and everything else is off. Or maybe that one is on and this one is on. So there's some attraction between these two chains. And then all of a sudden this one shuts off and this one turns on. Let's do it this way. And this one turns on. And then this one shuts off and this one turns on. And then this one shuts off and this one turns on, right? The longer the chain, the higher the chances that you have 2 on at all times. Or 3 on, or 4 on. And so this is why when we start going through in our brains, let's think about all of the organic chemicals that we have spent so much time talking about. Methane, CH4. Propane, C3, right? Butane, C4. These are all gases. Why are they gases? Because they're short chains, right? If you only have one carbon, is it always on? Is it always sticking? No, so it's probably a gas. Then we start switching to things like octane, C8, and you start getting liquids. because now they're getting longer. And there's more chances of there always being dipole forces at work. And then you go even longer, like say you go to something like C36. Not only do you have London forces always on, but you've now reached a point where you have tons of them that are always on. And we start getting things like asphalt, right? You start getting tar, you start getting candle wax, and those are always going to be solids. So the longer the chain is, the greater the chances of London forces interacting, and they can become very, very, very significant and very strong the longer the chain is. Now, the length of the chain is important, but it also depends on the shape, right? So for example, if we flip back to this, we see octane, actually let's do it like this. We see octane as two straight chains. But what if, for my octane, let me just clean this up a little bit. What if for my octane I drew it like this? 1, 2, 3, 4, 5, 6, 7. We'll go like this, right? If I drew an octane like that, how's my next molecule going to sit? Is it going to sit flat like we see right here, where we can have interaction here or here or here or here? No, all of a sudden, because of my shape, I might see something, right, that looks like this. And where's my interaction? Can the interaction occur from this distance? No. If this one gets a dipole on it, it can't reach across this distance to induce a dipole down here. It's too far away. So the shape matters. We find that really flat, straight chains are going to work the best. So we see over to the side here, something like these guys and something like these guys are going to have very different attractive forces, right? These are going to have more attractive force than these, because these have a flatter chain and more ability for them to sit flat and layer up against one another. Whereas the contact points, the amount of overlap that we can get between these guys is very, very small. So let's look at some of these effects now. Now that we see these intermolecular forces, what kind of questions are they going to be asking us on the AP exam? Well, one of the first things that they are going to ask us about is boiling points and melting points. This is the thing that I see asked most often. All right, so when we're looking at these effects, what they're going to be saying is they're going to be giving us a list of chemicals and asking us which is the highest, which is the lowest. Okay, so what we want to look for are all of the different types of forces that we're dealing with. Right? The more attractive force you have, the more difficult it is going to be to boil, and the more difficult it is going to be to melt. It's going to increase these values. So if you're ranking things, hydrogen bonds and ionic bonds, those are going to give us some of the most attractive force that we have. Right? If you see ionic bonds, that's the clear winner. Ionic bonds are solids at room temperature. They're crystals. They are really attractive. Once you start getting down into smaller molecules with only London forces, the attractive abilities are much less. Now, if it is very small, a hydrogen bond can be really significant, right? So it does tend to work best in small molecules, but most of the time when they're giving you items, they're very comparable. And so you're not going to see, a small one with a hydrogen bond versus, a large one with no hydrogen bonds, but just London. However, if you run into a situation where you see a really, really big material, understand that huge carbon chains, even though they may only have London forces, those London forces become extremely significant. and they oftentimes will outweigh even a hydrogen bond. So, for example, if you just had a carbon-carbon with LDF, London dispersion forces, and you compare that to an OH and another OH, right? This is a H bond. So you have two atoms, and you have two atoms creating, or I guess we could do it like this so that it's comparable. So say you have an ethane and an ethane, and then you have an OH and an OH. Who's the most attracted towards each other? We know that this one is going to be the greatest attraction, because really what a LDF is a really weak dipole. And this is a strong dipole. So the hydrogen bonding is going to win when it's an equal sized atom. But now if I add a whole bunch of carbons to these chains, and I say, oh, over here I have a weak dipole, and over here I just have these two little atoms, but they have a strong dipole. Who wins? This guy wins. Yes, the dipole is weak, but when you say weak times all of these atoms, it becomes very, very, very strong. And if they give you something like this, it's usually a really big difference in size. If it's only off by 1 or 2 carbons, then it's not significant enough. But if you have something with 12 carbons versus another element that only has 2 carbons and a hydrogen bond, the 12 is going to win. Okay, so remember, water is still just a liquid, right? It's not able to turn into a solid at room temperature. Now, viscosity, this is a term that basically is saying how well a liquid flows. So something like syrup has a lot of intermolecular forces in it, and so it's really thick and it moves very, very slowly, versus something like water, right? Or something like rubbing alcohol, or something like motor oil is even more viscous, right? So the viscosity is just describing not necessarily a phase change, but just how thick that liquid is. Surface tension is the molecules sticking together. We've seen this. We've talked about this with water. Hydrogen bonding is causing these molecules to stick together. Capillary action, we've seen this before as well. The idea that they can climb up a container because they're sticking to the glass and they're sticking to each other. But I'm telling you guys, the main thing that they're going to ask you about is boiling point and melting point. The type of question that you're going to see is going to often be referred to as either what has the highest vapor pressure, because remember, vapor pressure is an aspect of boiling. So when the vapor pressure is equal to the atmospheric pressure, items boil. So vapor pressure is basically when you have a liquid, we know that some of this liquid is always evaporating. Those evaporated particles are the vapor pressure. So if you have a lot of attraction, you might only have 3 things evaporating. If you have something with very little in the way of attractive forces, these things are going to escape very easily because they're not stuck together, so they're free to escape. So these things have low boiling points because if the atmosphere is pushing down with a lot of force, right, something like this is going to be able to match that atmospheric pressure pretty easily. So these have low boiling points, these have high boiling points. And so typically when we're talking about these things, there's a word that you might see them use is volatile. So if something has a high vapor pressure, or it easily evaporates, we say that it is volatile. Okay, so high vapor pressure. So these are going to be low intermolecular forces.